Hello everyone. Today we are going to solve a cool CTF lab from CyberDefenders. The challenge is called BlackEnergy. We have a memory dump from a hacked machine and we need to find the malware. I will show you how to use volatility to hunt for malicious processes and hidden drives. It's a fun lab with a lot of forensics. Let's jump into the terminal. Now to solve this lab, we are going to use volatility 3. It's faster and more modern. We need to know the operating system of this memory dump. In volatility 3, we don't need to guess the profile. We use a plugin called windows.info. Looking at the output, we can see the architecture. It's not a 64-bit system. This is a 32-bit. It's important to know this because our next plugins depend on the architecture. Now let's look at the major and minor numbers. The major number shows the main version of the OS, and the minor number shows a smaller update within that version. Based on the major number 5 and minor 1, we can identify this as the Windows XP. Another interesting detail in the output is the key number processors. This variable tells us the total number of CPU cores or processors in the system. In our case, it shows 1. This means the infected machine was running on a single core processor. We also have the system time. This is crucial because it tells us exactly when the memory dump was taken. In forensics, we always use this to build a timeline of the attack. Next, look at anti-system root. It's set to C Windows. This confirms where the operating system is installed. If we see a different path, it might be a sign of something unusual. Finally, we have the time date stamp. This shows when the kernel image was compiled. Question 2 asks, how many processes were running? Now we could use PS list, but in a malware case like BlackEnergy, we should use the PS scan plugin. Why PS scan? Because PS list only shows active processes by following the system's linked list, but PS scan scans the memory for processes structures, which means it can find hidden processes or those terminated by the malware. Let's run the command and count the total number of processes found in the memory dump. Before we count the processes, let me quickly explain what these columns mean. This is very important for any memory analysis. PID stands for process ID. Think of it as a unique ID card for every running processes. No two processes can have the same PID at the same time. It helps the system and us to track exactly which process is which. PPID stands for parent process ID. It's like a family tree. It shows us who started who. For example, if you open Notepad from CMD will be the parent. The image file name gives us the executable's name. Next is the offset, showing the virtual address in memory, followed by threads and handles that show the active tasks and resources used by the system. We also see the session ID for user sessions and WoW64 to identify 32-bit processes. Finally, the create time and exit time tells us exactly when the process started and ended, which we can then save into a file output for deeper analysis. Now, the question asks for the number of running processes when the image was captured. This is a very important detail because we used PS scan The list includes every process found in memory, even those that already closed. To get the correct answer, we need to exclude all processes that have an exit time. If a process has an exit timestamp, it means it's no longer running. So we need only count the ones where the exit time is empty. After filtering, we have exactly 19 running processes. Next question, what is the PID of CMD? We could find it using pscan, but this time I will use the pslist plugin to get the PID. Let's run it and locate CMD end list. To find it quickly, I used findstr to filter the results for CMD. The output shows us that the PID is 9060. It's a fast and efficient way to get exactly what you're looking for. The next question is, what is the name of the most suspicious process? Just by looking at the process list, one name immediately stands out: rootkit. In the world of malware, a rootkit is one of the most dangerous types because it's designed to hide itself and maintain deep access to the system. This is a huge red flag. Next question, which process shows the highest likelihood of code injection? To find this, we are going to use the most famous plugin for detecting malware injections. It's malfind. This tool scans the memory for suspicious permissions like regions marked as execute read write, which are common signs of injected code. Before we investigate the results, let's explain the malfind columns. We already know PID, but here we also have the start VPN and end VPN, which are the virtual address where the suspicious memory region begins and ends. While protection is the most important part because it shows the permissions like page execute read write. Commit, charge, and private memory give us details about the size and type of memory used. We also have the file output if we want to dump this for further analysis, and notes for extra context. After checking each process in the list, we can clearly see something suspicious with service host. Now, service host is a legitimate process responsible for running Windows services, but in this case, it contains a MZ flag. This is a huge red flag because MZ stands for Mark Speckle Scheme, the signature of a DOS executable. Seeing an executable header inside the memory of a running service like service host confirms that there is a code injection happening right here. The next question is, there is an odd file referenced in the recent process. Provide the full path of that file. To find this, we need to use the Handles plugin. This plugin shows us all the resources like files, registry keys that a process is using. Since we are looking for a file, we will filter the output by file. This allows us to see every single file the malware was touching when the memory was captured. Now we need to check the handles for any suspicious extensions. Malware often hides its code in a file types or folders where they don't belong. Looking at our list, we found a very strange file, str.sys. Seeing a .sys file, which is a system drive being used by a suspicious process, is a huge warning sign. This is likely our rootkit trying to hide deep inside the system. The next question is, what is the name of the injected DLL file? To find this, we will use the LDR module plugin. This powerful tool detects DLLs loaded in memory that are hidden from the normal Windows module lists. It's the best way to find a malicious DLL that's trying to stay invisible to the system. Let's run it and look for any false entries that indicate a hidden module. After searching through the output, we can clearly see a suspicious DLL flagged by the plugin, even though it looks like a normal system file. LDR modules detect it because it's hidden from the standard Windows lists. This is a classic move by malware to stay invisible to security tools while it runs its malicious code. The last question is, what is the base address of the injected DLL? To find this, we simply look at the base column in the same LDR module's output, where we found our suspicious DLL. This address tells us exactly where the file is loaded in the memory. For our case, the base address is 0x9A40. That's it. We found the malware, traced the injection, and uncovered the hidden DLL. This is how you handle memory forensics like a pro. If you enjoyed this investigation, like and subscribe for more. See you in the next case.